Thanks a lot for the introduction. So also appreciate the great efforts and invitation from the organizers. So today I'm going to talk a little bit about our recent work from Berkeley Deep Drive as well as the research team at Applied Intuition on how we can make the neural simulation more scalable for autonomous driving. So right now, the onboard stack for autonomous driving is migrating from more modularized kind of stack into more and more end-to-end differentiable stacks. And the question is how we can really evaluate or even train such kind of end-to-end stack with closed-loop simulation, which is driven by a large amount of data that we collected from the real world. And we can automatically generate reactive sensory inputs for such kind of end-to-end stack. And actually, neural simulation shows extremely strong potential and power for dealing with such kind of tasks. And some of the representative work includes 3D construction with Gaussian splatting or generative methods like diffusion models or even world models. But actually, our expectations for neural simulation is far beyond just utilizing large amount of data. There are several aspects that we want to consider. Of course, we want high fidelity of the generation with cross-modality and temporal consistency. We also want this to be more generalizable with strong controllability as well as robustness to not so well aligned sensory inputs. We also want this to be more and more self-supervised without too much human annotations, which can be pretty costly and inefficient. And last but not least, we want efficiency to be much better, both for the construction stage as well as the inference stage. We don't want to pay too much for the GPU hours for the reconstruction of the scenes when it goes to large scale. Well, we also want to have the online inference to be with super high throughput for really train our end-to-end model. So that's why we want to make neural simulation to be more scalable, working at the intersections of that. So first, let me talk a bit about the labelless part for one of our recent work. So actually, Gaussian splatting is showing pretty strong power in converting the multi-model stream into some reconstructed scenes that we can directly utilize for simulation. And recently, there are many interesting work, including the driving Gaussian, which is utilizing 3D bounding boxes for the decomposition of the static dynamic scenes, dynamic parts of the scenes. But actually, this can be pretty costly and inefficient procedure. And our question is how we can try to avoid having this for the 3D annotations while still having the pretty accurate decomposition of the static dynamic parts. And that's why we propose the Zhan, which is the 4D street Gaussian for self-supervised static dynamic decomposition, which can simultaneously reconstruct the surfaces as well with the normal depth as well as the meshes. And this is what we published in CVPR this year as well. So what we are doing is decompose into two stages. First is we implement some Gaussian splatting model to render the images from our data and taking advantage of some of the pre-trained 3D foundation model, namely FID 3D, so that we can obtain some feature map for both the rendered image from the Gaussian as well as the ground truth image. And then we can compare for the feature maps to obtain some feature similarity score for us to obtain pretty accurate dynamic mask. And in the second stage, we implement some dynamic Gaussian model, namely the periodic vibration Gaussian, so that we can render some velocity map. But this map may not be super accurate, and we can try to rectify it with a dynamic mask obtained from the first stage, so that we can have the corrected velocity map, which is pretty accurate, that we can directly decompose the static scene from it. And actually, we are also implementing some regularization for the Gaussian scale so that we can obtain pretty accurate 3D kind of information. For example, we are trying to penalize the minimum dimension of the Gaussian so that we can obtain some flat disk-like Gaussians. And we also penalizing the maximum dimension so that we can try to avoid having giant Gaussians, which can downgrade our quality. And then on the right-hand side, you can see how we can obtain pretty good flat disk-like Gaussians so that we can directly utilize for recovering 3D information, including the meshes as well as the depth. And here are some quick results that we can show. And on the top side is the ground truth image with moving vehicles, pedestrians on the road, or even on the sidewalk. And by implementing this RGS, we can accurately decompose the static part from the dynamics. And here is a quick video demo showing how good the performance is. So actually, Desire.js provides us pretty powerful tool for extracting the static parts and decompose the dynamic part from the in the 3D Gaussian reconstruction. But this is definitely not sufficient for us to create a perfect reactive generator in closed-loop simulation, because when we are trying to control the motion or behavior of the surrounding vehicles or pedestrians, there is a pretty obvious problem that we can observe for 3D Gaussian, which is incomplete views for the objects, for the parts that we haven't seen when we are trying to manipulate the vehicles with the side that we haven't collected data from to be towards us. It's pretty hard for us to render perfect kind of images. So how we can deal with such kind of problems? One of the straightforward way that we can take advantage of will be some off-the-shelf image to 3D models that can generate some 3D assets so that we can insert into the 3D reconstruction scenes. But the problem is, for such kind of asset, the quality or fidelity may not be super high or satisfactory, and the lighting of it, either on the vehicle or the shadows on the ground, may not be super satisfactory. And that's why we are thinking about how we can deal with this problem by enhancing the 3D asset with more realistic rendering and having more realistic shadow or lightings on the ground. So that's why we introduce R3D2, which is trying to create realistic rendering for the insertion of the 3D assets into the 3D reconstructed static scenes. And this is a joint work with our visiting PhD students at Berkeley Deep Drive. So whether or not it's the assets from the same scene, cross scene, or cross data set, or text to 3D, we can enhance that with diffusion model with significant improvement of the FID scores. So here is the some quick idea regarding the R3D2. So when having the ground truth images, we are trying to apply some mask for extracting the dynamic part of the images so that we can obtain partial view of the moving vehicles, utilizing some off-the-shelf image to 3D generator to have the complete 3D assets generated. And we try to insert that into the static part of the reconstructed scenes so that we can curate some data set serving as the input of some diffusion model. And we can use the corresponding image to serve as the ground truth for the supervision. And we design some one-step diffusion model utilizing VAE-based encoder and decoder to be trained from this curated data set to enhance the rendering for our data. And here are some quick results, and from which we can see that for the shadows on the ground, it can be pretty realistic after the naive insertion and applying the R3D2. And for the lighting on the surface of the vehicles, it can also follow the realistic kind of sand directions to render the corresponding lighting on the vehicle. And we are also allowing for more controllability while maintaining the realism, whether there are insertions from the cross-scene kind of 3D assets or cross data sets, having some vehicles extracted from another data set inserted to the other. We can always utilizing this for strong enhancement of the rendered quality. And there are even more controllability that we can allow. For example, the text to 3D. We can use the text prompt to generate the corresponding 3D assets and having the realistic kind of enhancement with the R3D2. And what is more important is that we can also arbitrarily rotate the vehicle with different kind of angles. For example, the 20-degree, we can still obtain pretty satisfactory kind of rendering. And some results that I want to show, even if we rotate the vehicles into like 180 degree with the R3D2, we can always enhance the fidelity significantly, either from the original reconstruction or the naive insertion that we are performing. And we also allowing different kinds of controllability for crossing, cross data set, as well as the text to 3D to obtain significant improvement of the fidelity. And here is an also interesting video that we created by utilizing the Waymo open data set. So here is the original video, and then inserting some 3D assets with 20-degree rotation, and then enhancing that with our R3D2 with pretty high quality there. So that is, we are showing we can have arbitrary kind of manipulation of the 3D assets in the data set. And a few more videos that I want to show for inserting some assets created from Waymo open data set into the Panda set here, as well as some even more controllability with the text to 3D, like the prompt with small blue pickup truck to be created, inserted into the Panda set. Okay, so now we show something related to how we can utilize diffusion models for enhancing something on top of the 3D reconstruction with the 3D assets. And actually, the utilization for diffusion models can be even one step further. That is directly generating multimodality, like raw data for serving the end-to-end kind of onboard stack with both multi-view images as well as the corresponding point cloud with input conditions like 3D bounding boxes or even the language prompts. And we are trying to ensure the consistency between the different modalities. And this is a work that we published in iClear this year. So different from some traditional paradigm, which is dealing with different paradigms of the data generation independently with the diffusion models. What we are trying to propose is to having the information exchanges between the two pipelines so that we can have consistent generation for both of the modalities for multi-view images as well as the depth information. A quick overview of the architecture. So for the two pipelines, which are denoising from the noisy range image latent as well as the noisy multi-view image latent, we are trying to have latent diffusion models to denoise that. And actually in the reverse process, for each of the step, we are trying to have the one of the modality to be conditioned on the correspondence from the other modality with the epipolar line, so that we can have the VAE decoder to directly decode either the synthetic range image or the multi-view image with pretty good consistency between each other. And here are some quick results that I want to show with the input conditions from 3D boxes, as well as some text prompts depicting the location, depicting what kind of scenario it is, or some potential behavior of the vehicles. And we can see that the model can generate pretty good consistency across different multi-views of the cameras, as well as in between the point cloud modality, as well as the multi-view camera modality. And some similar kind of situation settings that we have for different kinds of prompts or bounding boxes to be serving as the conditions, and they can still obtain pretty good performances there. And we can even go one step further to control the styles for rainy, for sunny, for night kind of style, or even having different kinds of number of the bounding boxes to reduce that into a half or increase the number with extra ones. And we can obtain the consistent kind of cross-modality consistency perfectly, as shown in those kind of images as well. Okay, so now we talk about how we are dealing with like different kinds of perspectives for the scalable neural simulation from the quality perspective as well as the labelless perspective and address controllability. And now let's switch the gear a bit for the efficiency side, as well as more about the generalizability, especially towards the 3D reconstruction kind of scheme with Gaussian splatting. So the work that I just mentioned, either the Desire.js or R3D2, the 3D.js like methods that we are utilizing is based on Gaussian optimization kind of paradigm, which is trying to optimize the Gaussian parameters directly for each of the scenes from the data that we have. And such kind of paradigm, when we are thinking about different attribute, different perspective of its attribute, from quality perspective, yes, it's pretty good. And from efficiency perspective, it's not so satisfactory because it takes at least 1 GPU hour to construct each of the scenes. For generalizability, it can only construct something that we have seen from the data log. And it can also be super sensitive for not so well aligned sensory input. And that's why we are thinking about how we can bring in some of our insights that we have learned from the onboard perception or other kinds of model design so that we can create some feed-forward network that can directly output some key parameters of the Gaussian ellipsoids and from the historical frames that we have obtained. And such kind of paradigm could have good potential for much better efficiency than the Gaussian optimization paradigm, although the quality is still to be improved. And for generalizability, it's also enabled with large amount of data trained with this one single model. And it's also can be with better robustness for unaligned sensory input. And due to the limit of the time, I will just briefly mention some of the representative work for feed-forward Gaussian for applied to the autonomous driving. For example, DrivingRecon, we're trying to introduce the 3D-aware positional encoding together with the temporal cross-attention with the Gaussian adapter decoding the parameters of the Gaussian with a feed-forward model, large feed-forward model designed for the autonomous driving applications. And we can see that for the Gaussian parameters that we obtained and then reports into the images for the objects and the scenes that is pretty far away from our ego vehicle, it can obtain much better performances than the other state-of-the-art feed-forward models for feed-forward Gaussian models for autonomous driving. And here is a quick view showing we are taking three frames as the historical ones, putting that into this feed-forward model, how we can generate the Gaussian parameters when we render that for each of the time step. And it can even with some more generalizability, although it's with pretty low resolution due to the limitation of the computation as well as the large size of the model. So there are still rooms for us to improve, especially considering the efficiency perspectives. And there is also another feed-forward Gaussian work called PixelGaussian, which is trying to challenge the uniform assignment of the numbers of the Gaussians to each of the image space pixels, so that we can take advantage of the existing uniform pixel-wise paradigm. Some Gaussians, we are just utilizing that as the initial ones to be optimized with some cascade Gaussian adapter, which can either split the Gaussians into more numbers or prune that to reduce the numbers, then with iterative Gaussian refiner so that we can obtain the Gaussians that can be adaptive for the numbers of different areas in the images. And it can be pretty clear that when taking a look at the areas of the images with more textual information, we need more numbers of the Gaussians. And our proposed method can obtain better performances than the other feed-forward Gaussian methods. And there are some areas which is pretty simple with the textures, and we need less numbers to review that. And for rendering a simple like table surface, it can also be with much better performances than the other method. Okay, so after talking a little bit about feed-forward model, actually let's go back to an even like higher level view, talking about how we are designing the models for both the onboard and offboard tasks, including the onboard differentiable stack towards tasks like perception, prediction, planning, or mapping. Some models that we can design for the feed-forward generation of the like reconstruction parameters, or even towards like more generative models or auto-labeling side. So for feed-forward Gaussians, we are taking advantage of many insights that we obtained from the onboard model design so that we can facilitate for more generalizable and efficient reconstruction for the offboard tasks. But let's think about it from the other way around, whether we can take advantage of the representation from the offboard construction side so that we can facilitate the onboard tasks as well, so that we can look towards some unified model design, model structure design, as well as unified 3D representations for both the onboard and offboard tasks. And this is also some thoughts that we have for paving the path towards some foundation models that can facilitate both the onboard and offboard tasks. And this is actually like pretty recent work that we have done at Applied Intuition research team from a research scientist, Zhan, as well as two intern students from Carnegie Mellon and Berkeley. So actually, we are trying to address this thought from dealing with some challenging onboard task, which is occupancy prediction, which is having the most like fine-grained semantic information for the 3D onboard task. We are trying to take advantage of something we have learned from onboard side, that is having the sparse queries to obtain pretty strong like runtime efficiency. And we are also like exploiting the like streaming structure, considering the temporal like inherent temporal nature for the for the data that we are dealing with. And we are also utilizing the representation from 3D Gaussian perspective for pre-training so that we can obtain much better performances. And for the occupancy prediction task, it can obtain much better performances than other state-of-the-art methods, as well as having much better kind of runtime efficiency. So here is the general architecture that we designed for the S2Go. So there are some like, it's a streaming architecture, and we are taking some past 3D queries, which can be pretty sparse. And our temporal transformer is taking such kind of queries together with the encoded features from the current images, as well as the randomly generated new 3D queries to generate the queries for the current frame. And then we decode that into like Gaussians that can be predicted and render the corresponding images. And we then splat that with the Gaussian to voxel splatting into the like occupancy prediction so that it can be supervised. But if we directly train such kind of architecture from scratch, actually it yields to some not so satisfactory performances, which is not quite comparable with the other state-of-the-art. So we are thinking whether we can introduce another stage, which is the pre-training stage, that we can either randomly generate some noised kind of input for the 3D queries so that we can have the denoised queries kind of pre-training together with the rendered depth maps and RGB images from the predicted Gaussians, utilizing the 3D reconstruction kind of thoughts that we have for the neural simulation, so that we can have much better performances than the previous ones. And here is a qualitative kind of intuition that we can show before and after the pre-training. The opacity of the Gaussian centers can be much more strengthened with this stage. And the performances of the occupancy prediction can go from not so satisfactory level directly to a pretty strong level. And such the S2Go structure that we propose can also obtain pretty strong performance even with the monocular camera kind of view on the KD 360 data set benchmark. So compared with the other state-of-the-art methods, we can obtain much better performances for the occupancy prediction. And on the new scenes benchmark, similar kinds of story, much better performances with even better kind of runtime efficiency. And actually, the sparse queries can also help us a lot for keeping pretty clear, good separation of the objects for the 3D occupancy prediction in comparison with the Gaussian world. We can directly and clearly separate the 3D the objects for the 3D in the 3D perspective. And here is a pretty long video that I won't play all across, but you can see that in comparison with the ground truth video on the right hand side, the occupancy prediction with our proposed structure, taking advantage of the 3D Gaussian representation can obtain pretty impressive results. Okay, so in addition to those methodologies that we have proposed, actually in applied intuition, we also productionized the neural simulator with the 3D Gaussian splatting kind of methods, which this is a scene that is near our headquarters. And there are also corresponding point cloud that is generated simultaneously. There are different countries that we are generating the neural simulation kind of reconstruction, or even with the off-road kind of scenes that we are generating. And I will also appreciate 30 seconds from you for having a quick promotion for our hiring. We have a research team working on different kinds of research topics, including neural simulation, world model, foundation model, reinforcement learning, post-training, as well as even agent AI and robotics. Actually, yesterday we also announced our partnership with OpenAI for different kinds of exciting kind of topic that we can work on. And we are hiring for different kinds of roles for the research team, as well as for our product team for neural simulation, for onboard stack, as well as ML infra. So a quick conclusion here, what we can have for the takeaway. So we are thinking about how we can make the neural simulation to be more scalable from 4 different perspectives, including the quality, generalizability, labeless, and efficiency perspectives. And we are also thinking about how we can unify the model design and the 3D representation for both the onboard and offboard tasks, so that we have working towards the foundation model that can be utilized for different kinds of tasks with large amount of data that we can obtain from the real world, so that we can have super efficient kind of inference for this model to serve either for the offboard construction as well as the onboard inference part as well. So I think I'm just right on time, and I'll just stop here for any questions from you. Thank you.